Thank you very much for introducing. I'm Yashar Sarafraz from Chair of Material Test Engineering at Technical University of Dortmund from Germany. And today I want to explain you and to show you the presentation of dimension-based failure analysis of foam internal thread in aluminum silicium cast profile using coupled destructive and non-destructive testing method. At first, we want to show you the introduction and motivation. Before I started to show you our manufacturing method, I want to show you a little about the cylinder housing, and in better magnitude, we can hear the internal thread, and due to this internal, we should consider a thicker profile and thicker by casting process to secure our internal thread. We saw a lot of investigation in direction of friction drilling parallel to the profile thickness. However, it's about the decade that the friction drilling will be performed perpendicular to the profile thickness by Institute of Manufacturing Technology. And you can see here, with this method, we can induce a higher number of threads in thin wall metal sheets and stronger joint consequency, and the possible work handling that can happen during the friction drilling and chipless manufacturing, that we can save the material. And after that, the internal thread forming, instead of thread cutting, we can have a fiber deformation, that we can have another work hardening and induce another work hardening in our thread profile, and from the other side, we can have another chipless manufacturing that help us to save the material. Our M6 internal thread was manufactured with three steps: pre-drilling, friction drilling, and thread forming process. This pre-drilling process was generated to avoid the possible failure on outer wall of our friction drill bore due to expansion by friction drill feeds. And our aims is, our challenge is oversizing of the bore by friction drilling in thickness direction, and that can affect our mechanical properties, dynamic and static properties. Aim is improving the quality of friction drill bore and thin valve component, and the investigation in these studies, investigating the influence of friction drill speed, peripheral speed, and feed speed, and diameter of friction drill on quality of the foam internal thread. Material that was used in this studies, general aluminum silicium alloy with 10% silicium content, and the other positive properties that due to lack of the time I don't say anymore. And we can see here the phase diagram of with 10% silicium content and the usual microstructure containing aluminum matrix, and in that the silicium particle in a needle form. The process parameter that was used for our process by using the CNC machines, you can see here our specimens between the jaws. Pre-drilling was constant with a diameter of 2.5, and we changed the diameter in friction drill from 5.4 to 5.5, and another thing that we changed is using a dynamic tools speeds, both tools speeds, and we reduced it for 25% at the beginning of the process by penetrating this conic shape in material, and after that we increased it to a normal speeds. And the thread forming process that was performed with the constant process parameter, as you can observe in this table, and at the end we can have this thread that you can see from the top of the thread. Experimental setup that was used in this study is a dimensional methodology that was used by CT scan by capturing the voxel of this created thread using this process parameter. And after that, analyzing of our captured voxel dimensional methodology using VG Studio Max to measure the volume of the created bore and thread using the defect volume analysis. Additionally, the tensile lymphatic test was performed in these studies. With this process of parameter tensile test was performed by engaging the 4 initial thread profile with steel rod, and for fatigue test, you can see here we use the ACPD method, and in a tension, in a SS ratio in tension region and a frequency from 10 Hertz, you can see we use thermocouple to measure the deformation-induced temperature by putting the thermocouple near the 4th and 5 thread, where we can estimate the higher deformation, or sometimes from the side of the specimens near this 4th thread. Result and discussions, you can see here the measured volume in friction drill bore. The first things, the volume can be observed in orange colors, and sheet diameter was measured in top, middle, and bottom in a 4 millimeter length. The first thing that we can see that all evorces in the drill bore in cross direction located because of the thickness, reduced thickness in comparison to longitudinal directions, and high roughness that can be observed. Here is another thing that bulging in cross section is another thema that can be observed here. After that, we can see here in diagram the compression. We can see by increasing the friction drill diameter, we can have an increase in volume generally, but however the deviation from the tools diameter that you can see here in dashed line, red line, is not different between them. And the thing that we can observe here is the expansion, the maximum bore diameter at the top of the specimen, that shows that at the top of the specimen is expanded from both sides. And by using the adapted speed and reducing the friction drill speed at the beginning of the process, we can receive a lower volume in comparison to friction drilling with constant speed. The experiment was followed by measuring the volume in the created thread for 4 initial thread, 4 millimeter as a standard pitch for M6 internal thread, and you can see due to reduced thickness in this direction, cross direction, the lack of enough material decreases the support in cross direction, and we can have a knot dilation during the thread forming process. Therefore, the material flow will be done insufficiently, as you can see. Therefore, we can have a not complete formed thread, especially in cross direction in comparison to longitudinal direction, that most of the thread was formed completely. Comparing the measured volume, another time we can see that our thread was oversized by increasing the friction diameter. However, it was not observed a significant change somehow in opposite of the friction drill. We can have an increase in increase in volume of created thread by adapted speed by friction drilling. Meteorographic analysis was performed for both constant speed and adapted speed. 2 deformation region was defined in this. The first region is region under shear and expansion, that the material was sheared by tools rotation and was accumulated in cross direction. Therefore, we can have a higher thickness. This red color region is responsible for sheared and expanded material, and the other place here, the second region is the material just only expanded in cross direction. It was not observed any difference between them, constant speed and adapted speed. The microstructure analysis was continued by thread. In a bigger magnitude, we can see that thread was completely located in cross direction in friction regions, sheared and expanded region. However, the thread was not completely formed, but in longitudinal direction, we can see that the friction region only limited to a small line in the middle of the thread tip. The tensile test was performed. You can see here the curve, linear curve, force elongation curve, and the Balkan diagram. We can see that we can have a reduce in maximal achieved force by increased friction diameter, and however we can see that we can receive a lower quasi-static strength by adapted speed in comparison to constant speed. And the other thing that we can say that this change of in elongation at break that is lower in comparison to constant speed that which can be justified in an increased work hardening resulting from reduced tool speeds. Adaptive speed has a significant influence on elastic plastic deformation and the elongation at break by tensile test. Here we can see the CT scan after break, after fracture by tensile test. We can see by constant speed we can have a shred stripping that we can observe here and here by reduction in the critical shear plan of the shred proofing caused by shred bending and not dilation that we can see here high deflection of shred thickness directly by subjecting under lateral force, not dilation. However, less dilation was observed by adapted speed, and you can see that the lower deflection of the nut in thickness direction, and we can see that in comparison to this method that shred is shear off from the bore, we can see that the crack is initiated in 45 degree and was propagated in radial directions. The load increase test was performed using the thermocouple to measure the deformation induced temperature. You can see that we can see by increasing load increases by increasing the maximum force. We can have at first we can have a decrease, a slight the temperature decrease at the beginning of the test due to high deformation required to smooth the roughness on the third flank, and after that we can have a linear trend, and at the end by increasing the deformation, we can have a exponential increase in temperature, deformation induced temperature actually. And the fractographic analysis you can see here by that was performed for us a specimen. We can see here that the fatigue fracture was initiated, was continued up to the friction region. After that, we can have an abrupt fraction that shows of this friction region shows a better strength in comparison to cast material. You can see here actually the fracture that was performed was occurred during the fatigue test. Sorry. In this slide we can compare it in the Balkan diagram. Another time we can have a decrease in increased fixture diameter, and we can see this time opposite of tensile strength, we can have a better dynamic strength for our adapted speed in comparison to constant speed. Using the ACPD method in combination from temperature in the deformation induced temperature can observe better in fatigue test, not load increase test. To compare it, we can see we cannot observe a significant change in plastic strain amplitude and the total mean strain. However, we can observe the change in temperature and change in potential. To understand it better, we can see this run-out force for our experiment, and we can divide it at the first. We can see that we can have a inadequate contact at the beginning due to flank roughness resulting from thread forming. That we can have an increase in change in temperature, and after that will be decrease in the second, decrease in potential by increasing the contact surface and smoothing the roughness, resulting electrical and reducing the resulting electrical resistance that we can have decrease the minimum value. And after that, by not dilation, we can have a decrease in contact surface and increase in resistance consequently that we can see here. And in the fourth step, we can have a crack initiation in shred profile, small cracks, and following cross-section reduction that can lead to a resistant increase and increase of the potential up to an infinity value. It's the last. Summary and outlook. I explained we observed that the increase in friction diameter can decrease our static and dynamic properties. It was not observed the opposite behavior by adapted and constant speed in tensile test and dynamic test, and the proper correlation of the NDT method with each others that was observed. And you can read these papers to have a knowledge about our method, and thank you from DFG for funding this project and Institute of Manufacturing Technology to manufacture our specimens. Thank you very much.